Good morning. This is class 3 on our unit 4 magnetic properties of solids. Today we will discuss about the temperature dependence of saturation magnetization and saturation magnetization at absolute zero. So in the last class we have discussed about ferromagnnetic material in detail, right? Now consider one such ferromagnnetic solid having n number of atoms per unit volume, and let each of these atoms possess a total angular momentum quantum number, capital letter J. Okay, then the expression for magnetization can be written like this: M is equal to N G J mu B Bjx. That is your equation number 1. This we have already written in one of our classes. Now here Bjx is a Brillouin function. It is given by this expression, and here x, you can see an x here. It is given by this expression. Here B effective is equal to B plus lambda m. B effective is nothing but effective magnetic field on an atom or ion. It is given by B effective is equal to B plus BE or B plus lambda m. And here N, as I already said, it is a number of atoms per unit volume. G is the Landé G factor. Capital T J is the total angular momentum quantum number. Mu B is the Bohr magneton. Okay, so you have two equations, equation 1 and equation 2. In case of spontaneous magnetization, what is spontaneous magnetization? Magnetization in the absence of external magnetic field. So B will be equal to 0, right, in case of spontaneous magnetization. Now you substitute this value of B as 0 in equation 2. Then your equation 2 will become, that is, here you just substitute the value of B as 0. So your equation 2, that is x, will become G J mu B lambda m by kT. From there you can write the value of m. Okay, mt means magnetization at temperature T. This m is equal to x kT by Gj mu B. Okay, x kT by lambda Gj mu B, equation 3. Now when temperature tends to 0 or when x tends to infinity, Brillouin function Bjx will tend to 1. That is, the magnetic moments will align themselves parallel to the field. That is, magnetic moments will align in the direction of field, and the magnetization M will become saturation magnetization. That is why it is written MS. S stands for saturation. Okay, saturation magnetization, and it is represented as MS0 because it occurs at temperature T equal to 0. Then saturation magnetization becomes saturated, that is, it will attain its maximum value. So that's why you are putting here the value of T as 0. So this is saturation magnetization. Then from equation 1 we can write MS0 as Ngj mu B. Okay, that is equation 4, because equation 1 was this one, right? Ngj mu B Bjx. Bjx becomes 1. So M will be Ngj mu B. Okay, so equation 4. Now just from equation 3 and 4 we can write, that is, just divide equation 3 by equation 4, that is mt by ms0. Just divide this by this, then you will get equation 5. And after that, from equation 1 and 3, that is, you just divide equation 1 divided by equation 3, then you will get equation 6. That is very simple. You can just write here, this is your equation 1, mt divided by ms0. Okay, so you will get, everything will get cancelled, you will get only Bjx. Let that be equation 6. Now the magnetization MT, that is magnetization at a given temperature, that is what it is written as MT. Okay, now you can obtain that value of MT by solving equation 5 and 6 simultaneously. And the plot of MT by ms0, this one, that is MT by ms0, okay, versus X representing equation 5 and 6 are shown in the figure given below. See, this is the curve corresponding to equation 5. Then this one is the curve corresponding to equation 6. And all this happens, that is the plot corresponding to equation 5 and equation 6 corresponds to temperature T less than Tc. This is a straight line at T equal to Tc, and this one is for T greater than Tc. Okay. So these are the various ranges they have shown for this particular ratio. This plot is important, so please draw this figure. Also, this one is also important, so these two plot you have to draw. Note that equation 5 represents a straight line passing through the origin and having slope proportional to t. That is, see, equation 5, it is a straight line, okay, passing through the origin, and it is having a slope proportional to temperature T. Now at temperature equal to critical temperature, that is Tc, what happens to this line? This line is a tangent to the Brillouin function at the origin. Okay, see, at that is this one. At T equal to Tc, Tc is a critical temperature. What happens to that straight line? It becomes a tangent to the Brillouin function at the origin. The intersection of the 2 points at the point O, the intersection of the 2 points at the point O, this one, the origin, represents a positive solution, but magnetization corresponding to this point is unstable. Okay, now what is another point of intersection? Another point of intersection occurs at T less than Tc. See this portion. At T less than Tc, another point of intersection occurs, and it indicates a non-zero value of M even for zero external field, and hence corresponds to spontaneous magnetization. Hope that sentence is clear. We have got two point of intersections, one at here and the other at here. That is, one occurs at T equal to Tc and the other occurs at T less than Tc. And at this point, magnetization is having a non-zero value, but magnetic field is zero. That is, even though magnetic field is zero, you are having a non-zero value of magnetization, and that's a condition for spontaneous magnetization, right? Okay. Now it also follows that spontaneous magnetization decreases with increase in temperature, and it will vanish beyond the temperature Tc, that is critical temperature, which is known as ferromagnetic Curie temperature. This we have already said. Now the variation of spontaneous magnetization with the temperature is shown in this figure. This is the figure. So this figure is also important, and also its explanation. Now it becomes maximum. Okay, that is, spontaneous magnetization becomes maximum at 0 Kelvin when all the moments are lined up in a particular direction under the influence of exchange field. The variation of Ms enables one to classify paramagnetic ferromagnetic transition as a second order phase transition. Okay, so what the significance of this figure? That is, this figure shows the variation of spontaneous magnetization with the temperature, and what is its significance? This one, that is, we will be able to classify the paramagnetic ferromagnetic transition as a second order phase transition. Okay, then let us discuss briefly about the paramagnetic region. Consider the magnetization in the region well above Curie temperature. Okay, when that is, the spontaneous magnetization or ferromagnetism exists below Curie temperature, right? When the temperature is increased above Curie temperature, that is when T is greater than Tc, you will have paramagnetic region, or the ferromagnetic material will become paramagnetic. Okay, now we are going to discuss about that temperature region for T greater than Tc. Okay, what happens? Spontaneous magnetization is 0, and an external field has to be applied to produce some magnetization. Okay, now this field that we are going to apply should be weak enough to avoid saturation state. So in such case, from equation 2, if x is very small compared to 1, our Brillouin function will take this form. Okay, therefore your equation 1 will become, what was your equation 1? M is equal to NGJ mu b bjx. Okay, in place of that bjx, you have to substitute this value. Okay, so your equation 1 will become like this. Then from here you can write the value of x. Just rearrange the terms, so you'll get this equation. Okay, thus m is equal to substitute the value of, that is this is the value of m that you obtain by substituting the value of bjx as this in equation 1. So you will get this equation, and after that you have already written an expression for x, right, in the beginning. That expression is written here. Now you just substitute this value of x here, then you will get this value of m as this. That is the way how you have to think. Okay, first you have an equation m is equal to n g j mu b bjx, right? So it's for bjx, under this condition bjx is having this value, so you just substitute this value of bjx in equation 1. So your equation 1 will become like this. Now you have already written an expression for x like this before. Okay, substitute this value of x here, then your m will be reduced to this. Okay, hope it is clear. Now which will give chi, that is susceptibility, equal to mu 0 m by b, which is again equal to mu 0 tc by lambda t minus tc, or chi equal to c by t minus tc. Chi equal to c by t minus tc. This equation is very important, that is equation 7. Here they have skipped a few steps. No matter, instead of writing all those steps, you just write what is written as such. Okay, after writing this you can directly go to this expression. Here c is equal to mu 0 tc by lambda, that is here they have replaced it with the letter c. Okay, and critical temperature Tc is n lambda n g square mu b square j plus 1 by 3k, and this equation 7, that is chi equal to c by t minus tc, is known as Curie-Weiss law, and it describes temperature dependence or susceptibility in a parametric region provided temperature is well above Curie temperature, that is condition T greater than Tc. Okay. Now Curie temperature determined from theory of spontaneous magnetization differs by a few degrees from experimentally determined value for parametric region. No need of writing that sentence. It is enough you stop by writing to here. Okay. Okay, so this is easy to learn. There is not much confusing. So only thing is you have to study a few equations as such. This, I think this one you will have to learn. There is no other way. The rest everything we have obtained by substituting those values. Okay, so just work it out one time, then it will be easy for you to understand. Okay, thank you.